Welcome back, ladies and gentlemen, to another exciting JLand Bio video. Today, our focus for Integrated Chemistry Physics, video 3-2, we are going to be focusing on the conservation of energy, temperature, thermal energy, and heat. So our real focus today is understanding how energy changes form. We need to make sure that we understand that it is neither created nor destroyed in the process, but rather just changes what type of energy is present. And then we'll also talk specifically about the relationship between temperature, thermal energy, and heat. Let's take a look at our student learning objectives for today. By the end of this video, you should be able to understand and explain the law of conservation of energy. You should also be able to explain how energy and power are related to each other. You should be able to differentiate between temperature, thermal energy, and heat, as well as calculate changes in thermal energy. So let's talk about something very important in the world of science. And that key concept is that energy can neither be created nor destroyed. It can only change its form. So let's consider a roller coaster. At the very top of the roller coaster, you have an enormous amount of potential energy, but very low kinetic energy. Usually very, very high up. So you have an enormous amount of potential energy that can be released as you go down the roller coaster and converted into kinetic energy. You have very little kinetic energy at the top because you're barely moving. As you roll down, that potential energy gets converted into kinetic energy. So energy never really is created or destroyed. It just simply changes whatever form it's in. Now, mechanical energy is specifically the sum of the kinetic and potential energy of an object in a system. Consider a falling object. Let's say it's an apple from a tree. An apple that's attached to the tree has high amounts of potential energy but low kinetic energy because it is not moving. If the apple, for some reason, is too heavy and then falls, all of that potential energy is converted into kinetic energy. So really, the energy itself is neither created nor destroyed. It just simply changes its form based on what's taking place. And in this instance, mechanical energy, we're looking at just specifically kinetic and potential energy. But there's loads of other different types of energy that are out there, which we can transform into different forms. Energy transformations also occur during projectile motion when an object moves in a curved path. Consider a hit in baseball. When the ball is initially hit, there's a lot of kinetic energy. As it reaches the peak of its arc as a projectile, once it gets to the top of its projectile, it has very low kinetic energy and very high potential energy because of how high it is off the ground. As the ball then starts hurtling back towards Earth due to gravity, that then potential energy is then converted back into kinetic energy as it approaches the ground. So again, lots of different ways that we can look at this, but understand that energy within the system is always constant. It's just changing whatever form it may have from potential to kinetic. Other versions of energy transformations, think about the effect of friction on an object, right? If you rub your hands together, you're taking the kinetic energy that's in your hands from the movement of that, and you're actually converting it into thermal energy, which is why your hands feel warmer when you rub them next to each other. How about transforming electrical energy? Batteries have chemicals inside of them. The movement of those chemicals through what's called a voltaic cell actually convert the chemical energy that exists within those individual atoms and molecules and convert them into electrical energy. Or even transforming chemical potential energy from the food that we eat or gasoline. There's tons of energy that is present in them. And then when we eat the food, our body converts that into energy that can be used for other processes. While gasoline, the energy in the bonds there, is used to move your car. So lots of different types of energy transformations are available. Power. Power is simply how fast energy changes or transforms. Think of a power hitter in baseball. You have kinetic energy going one direction, and then as soon as the ball is hit very, very hard, changes direction with an enormous amount of energy. Power is measured in watts and is equal to the energy in joules divided by time. Fairly easy way to go through and calculate that. Let's do a practice problem. So you transform 950 joules of chemical energy into mechanical energy to push a sofa. If it took you 5 seconds to move the sofa, what was your power? Well, remember that power is equal to energy over time. And so we are given energy in the problem, and we are also given time. So we can simply solve for power by plugging in those numbers. So we'll take 950 joules, and we're going to divide that by 5 seconds. And the power that we get out of that is 190, and remember our unit is watts. Again, another fairly straightforward formula for you to use in order to be able to solve for an equation. Let's move on. Temperature and thermal energy are very closely related to each other. Temperature is just simply a measure of the kinetic energy of the particles, and we typically use this in science as degrees Celsius or Kelvin. One thing to keep in mind is that temperature is not heat. Heat is the transfer of energy from one object to another. Temperature is the measure of the average kinetic energy of the particles, so as a result, if there is more energy, the particles are moving at a faster rate. Thermal energy is the sum of the kinetic energy and potential energy of all the particles that make up the object. So even objects that appear to be solid, those molecules do have movement that is associated with them. Liquids and gases obviously would move faster because those occur at higher temperatures than solids, but hopefully you get the idea. Remember that heat is a transfer of energy between objects, not temperature. So mass and thermal energy are directly related to each other. Think of a glass of water versus a small cup. It's going to require more energy to get a larger amount of water to boil than it would a smaller amount. It makes sense. The waters in both beakers are at 100 degrees Celsius on the right-hand side. Beaker B is going to cool off than Beaker A because Beaker A would have more thermal energy. So while it would take a longer time to bring water in Beaker A to a boil because it has more material, it has more mass, and therefore would require more energy to transfer in order to get those molecules to have high kinetic energy, Beaker B cools off quicker because Beaker A has more thermal energy. And again, heat is just simply the transfer of energy between objects. Energy always transfers from warm to cold. So for example, my hand is on a cold desk, so energy is being moved from my hand into the desk. That is why my hand feels cool, and then the desk eventually begins to warm up. The specific heat of a substance is the amount, the specific heat of a material is the amount of heat needed to raise the temperature of 1 kilogram of the material by 1 degree Celsius. Having different materials results in different abilities to absorb heat. Some things absorb heat better than others. So for example, liquid water there actually requires the most energy in order to raise it by 1 degree Celsius. If we look at lead, copper, iron, they have very low specific heats. And what that means is that it's very, very easy to raise their temperatures. It's very, very difficult to raise the temperature of water because it absorbs heat very, very well. Now there is a calculation that you can perform for thermal energy change. The change in thermal energy is equal to the mass in kilograms times the temperature change in degrees Celsius times the specific heat. Or Q equals M times the final temperature minus the initial times C, which is your specific heat. Or, as we like to call it in chemistry, Q equals MC delta T. The temperature change is always your final change minus your initial, so you may get a positive value, you may get a negative value, depending on whether your temperature increased or decreased. Let's look at a practice problem. A wooden block has a mass of 20 kilograms and a specific heat of 1,700 joules times over kilograms times degrees Celsius. Find the thermal energy change in the block as it warms from 15 degrees to 25 degrees. Well, we know we're going to be calculating the thermal energy change, so that is going to be Q equals M times the final temperature minus initial times the value for C. So we have our mass, our specific heat, our initial temperature, our final temperature. We can then solve. So Q equals M, 20, change in temperature, so 25 minus 15, and our specific heat, which is 1700. All we do is we simply plug in and solve for Q. So we end up with a value for Q of 340,000. And because we're talking about heat and energy, we will use joules as our unit. So again, these problems are fairly straightforward. Just identify what variables you have, identify your unknown, and then plug in and solve appropriately. Pretty straightforward material today, guys. Make sure this is the end of the video. You should be able to understand and explain the law of conservation of energy, explain how energy and power are related, differentiate between temperature, thermal energy, and heat, and calculate changes in thermal energy. That's it for this week. I hope you guys have a great day, and we will talk to you later. All right? See you later. Bye.